Hey, 7th graders, it's Miss McGowan. I'm getting ready to attempt to teach your first lesson. We're going to be doing Chapter 9, Lesson 2. The title of the lesson is Theoretical versus Experimental Probability. Here is just a quick shot of the lesson and the materials you're going to need. You're going to need your math book, and you're going to want to start at page 724. We'll be working from 3 pages. And then you're going to need a pencil and a calculator, okay? So you can pause this and grab all those things if you'd like to before we get going. What I'd like to do is, instead of doing the examples from the book, I'm going to try to get a little creative, and I'm going to use Sign Wheel to help me here in just a minute, but we're going to actually learn what theoretical versus experimental probability is using some real life situations, okay? Just to explain the difference, theoretical probability is what should happen based on the odds in a situation, okay? Experimental probability is what actually happens. Now, if you think back to the last lesson we had before school got canceled or postponed, we had learned that probability is how probable or likely an event is to happen based off of the outcomes, okay? So when we look at theoretical probability, it's basically looking at the odds of something happening, okay? But we know that things don't always happen the way we would think they might happen. We see this in sports all the time. There's a team picked to win it, and there's some kind of terrible upset, even though theoretically on paper, all year long, that would have been the better team. But then when it comes down to the actual game, the other team wins. So theoretically, team 1 should win, but when the actual game happened, in the actual so-called experiment, the other team wins. Typically, your experimental probability should be the same as your theoretical probability or close to it. If it's not, it's probably because there have not been enough opportunities. So if we flip a coin, which is going to be one of our experiments, 10 times, we can assume theoretically that half the time, if we wanted to know the probability of getting heads, we could assume half of the time, or 1 out of every 2 tries, would be heads, because there are 2 outcomes and one of those are heads. So that's going to be one of the experiments we do with the boys in just a second. I'm going to keep a tally, okay? But theoretically, we know that 1 out of every 2 tries should be heads, okay? That's what ought to happen. So if I'm going to flip that coin 10 times, we can assume that 5 out of those 10 would be heads as well. Now, that may not be how it ends up when we do the experiment. But if we did this instead of 10 times, if we did it, say, 1,000, I bet that we would find that it was a lot closer to that theoretical probability. So sometimes if your experimental and theoretical probability are not close, the reason for that can be that there were not enough tries. One other thing to mention to you is that in probability, percentages are used a lot. So we could convert 1/2 into a percent by changing it to a decimal using division. Top dog gets the house. So 1 divided by 2 is 0.5. And then when we shift that decimal point 2 places to the right, that would end up making it a 50% chance, theoretically, that we're going to get heads. So in just a moment, we're going to test this out. We're going to do 10 tries and see if our experimental probability lines up with our theoretical probability. We're going to compare them, okay? The other experiment we're going to do has to do with these 4 candies in this bowl. There are blue, orange, pink, and green. Now, in just a moment, I'm going to have the boys randomly choose a candy 8 times, okay? Now, theoretically, because there's 4 different colors, if I wanted to know the probability of choosing blue, I would say that there is a 1 in 4 chance of that. There's 4 possible outcomes. One of them is blue. So I would say that there is a 1 in 4 chance, Or if I change that to a decimal and then convert that to a percent, that would be a 25% chance of choosing blue. Now, when we actually do this experiment in a moment, we're going to get our experimental probability results and we're going to compare those as well. Okay? So just to kind of recap, theoretical probability is what should happen based off the number of outcomes and the possibility of one specific outcome happening, where experimental probability is what actually happens when the experiment is conducted. Okay? So I'm going to pause the video and I'm going to go to sign wheel. I'm going to keep track of those and we'll come back together and figure out the experimental probability. All right, this is a side wheel. They're going to kind of help me conduct this experiment. I've got my little tally going here. We're going to do a total of 10 flips, so each one of them is going to flip 5 times. I'm keeping track, and we're going to then figure out what our experimental probability was. Okay, so guys, here's what I'm going to do. I'm going to say flip. When I say that, you flip it, and then I'll ask you for your results. We'll do that 5 times, okay? All right, go ahead and flip. All right, Will, what'd you get?
Tails.
Si?
Tails.
All right, flip. Will?
Heads.
Heads.
Tails.
Si, tails. All right, flip. Will?
Heads. Tails.
All right. That's a total of 6 times. We've got to do 2 more flips each. Go ahead and flip. Will?
Tails. Tails.
Okay.
Dang.
All right, 1 more flip.
Tails. It is tails.
Okay.
Tails?
All right. Thanks, guys. Okay, so I'm back with the second experiment. The results from the heads and tails, we'll come back to that in just a second. So again, we have a blue, orange, pink, and green candy in the bowl. We're going to do 8 tries, and we want to know what is the probability that we're going to get blue. That's going to kind of be what we're looking for here. So boys, I want you to take turns. I tell you what, Will, why don't you pick one and put it back in and do that 4 different times. I'll record your results and then switch and so I can do it. Okay, so go ahead.
Blue.
All right, put it back in. Mix them up, pick another one.
Green.
Okay.
Green.
All right, 1 more for you.
Orange.
All right, now switch with Si. All right, Si, you ready? Come on.
Blue.
All right. Let's go.
Pink.
Okay, 2 more. Make it quick.
Pink.
All right, 1 more.
Orange.
All right. Thanks, guys. Okay, guys, I'm back with the results from our 2 little experiments. So here were the results from the heads and tails experiment. So if you notice, out of the 10 tries, heads was flipped twice, while tails was flipped 8 times, okay? So if we wanted to get our experimental probability, what actually happened, okay, then we would say, since we were focusing on heads, the probability of flipping heads, then we would say 2 out of 10, I'm going to write this down for us, 2 out of 10 times, which simplifies to 1/5 of the time when I reduce it to its simplest form, okay, was the actual experimental probability. Now, if we convert that into a percentage, we know that we can divide 5 into 1, which gives us 0.2. And when we shift our decimal point 2 times to the right, that ends up being 20% of the time, okay? So now let's compare these. Theoretically, if I was going to flip a coin 10 times, 50% of the time, it would be heads. Theoretically, in theory, that's what should happen. But when we actually tested it out this time in this trial, we only got heads 20% of the time. Now, a possible explanation for that, the odds are still the same. There's still a 50% chance that if we flip a coin 10 times, 50% of it would be heads. But in this specific experiment, that didn't happen. However, if we were to continue more and more trials, if we were to do this, like we said, 100 times or 1,000 times, over time, we should start noticing that experimental probability is getting closer and closer and closer to that theoretical probability, okay? Because a saying among people, math teachers, really just in the world, is numbers don't lie, okay? If you do something enough times, statistically, the probability of what should happen should eventually line up with what really does happen, okay? So the explanation for this could be we just didn't do enough tries, okay? Let's look at the candy experiment. So it actually ended up exactly like we thought it would based off the theoretical probability. There were 4 candies. We wanted to know the probability of choosing blue. We got blue 2 times out of 8. Okay, so that was actually what it happened in our experiment, 2 out of 8 times, which reduces to 1/4, which when turned into a percent is 25%. So in this experiment, we actually noticed that our experimental probability and theoretical probability are the same. Now we could turn around and do these exact same experiments the next time, and they may be the same, they may not be, but over time, if we did it enough, we would find that our theoretical and experimental probability would probably get closer and closer and closer. So I am about to pause the video, and I'm going to get my book pages ready, and then we're going to work together a few examples, just maybe like 10 minutes or so, of some problems from the book so that hopefully you guys have an idea and concept of what theoretical probability is versus experimental. What should happen based off the number of outcomes versus what actually does happen. Okay? See you in a minute. Okay, guys, I'm back and I've got my math book set up. I so wish you could see this little redneck setup that I have involving cardboard boxes and everything else I could find to rig my phone up here to video my math book while I work with you guys. But we're going to actually take some time now to work some problems from the book. I'm on page 724. I have my calculator handy, and we're going to start with number 1 on the guided practice. It says a coin is tossed 50 times and it lands on heads 28 times. Find the experimental probability and the theoretical probability of the coin landing on heads. Then compare the experimental and theoretical probabilities. I like to start with the theoretical probability because it doesn't require an experiment, okay? So just like we did with the boys, because we're doing a coin toss, there are 2 possible outcomes. One of those is heads. So we know there's a 1 in 2 chance of flipping heads, okay? If we convert that to a percent, we know that 1 divided by 2 is 0.5, which is the same as 50% of the time. So 50% of the time, we should get heads. Now, our experimental probability is going to be what actually happens. So it says the coin is tossed 50 times, and out of that, it lands on heads 28 of those 50 times. Now, we could go ahead and immediately convert this into a percent to check it out, or if we would like to, we can simplify this first. We can divide both 28 and 50 by 2, and that's going to give us 14 25ths, okay? And now I can come to my calculator, and I can do 14 divided by 25, which gives me 0.56, move my decimal place 2 places to the right, and that's 56% of the time. Now, when we compare these, we can say these are close enough, okay, to each other that would be, we could say, an expected result. So we're just simply going to say the theoretical probability is close to the experimental probability. And I'm kind of abbreviating that for you. All right. Now, the other thing that we can do concerning these events and the probability or likelihood of them happening, and this happens all the time in real life, is we can use the probability of events that have happened in the past to predict the probability of them happening again in the future. And I'm going to show you two different ways we can do it. Okay. One is using proportions. Number 2 says, yesterday, 50 bakery customers bought muffins, and 11 of those customers bought banana muffins. If 100 customers buy muffins tomorrow, how many would you expect to buy a banana muffin? So the first way I'm going to show you is using a proportion, okay? We can say, all right, well, yesterday, 11 out of 50 people bought a banana muffin. Okay, I can use that ratio to predict how many people would buy a banana muffin out of 100. So again, I have this set up, banana muffins out of total muffins yesterday, banana muffins out of total muffins tomorrow. So I'm going to use this ratio here to find how many people would probably buy banana muffins tomorrow. Now you can see there's an obvious times 2 relationship here, so you should probably mentally immediately see that it would be about 22. But if you don't, you can always use your cross products and write a little equation. 50x equals 1100, and then divide both sides by 50 to get x by itself. And when you do that, oops, let me clear my calculator again. You're going to get 22. X is equal to 22. So we can assume or predict that 22 people would buy banana muffins tomorrow. Here's the other way you could do this. Last year I had a lot of kids that preferred this way, and I'm just going to kind of do it down here at the bottom. You can take your original ratio, 11 out of 50. You can use division. I'm going to do that right here for you. 11 divided by 50, and turn that into a percentage. So we get 0.22. If we shift the decimal 2 places to the right, we're going to say that 22% of those muffins were banana muffins. So then you can say to yourself, okay, well, tomorrow there's going to be 100 muffins sold. What is 22% of 100? So you can actually turn this into a percent problem and then do 0.22 times 100, and you're still going to get the 22. So that's just going to be personal preference. Do you like the proportion, or do you like to get the percentage and then apply that percentage to your number to make your prediction? Okay? All right, let's move on to number 1 on the independent practice. I'm going to kind of let the clock dictate how many of these we do. I don't want it to be too time consuming. Number 1 on page 725 says a number cube is rolled 20 times and lands on 1 2 times and on 5 4 times. Find each experimental probability and then compare the experimental probability to the theoretical probability. Let's start with our theoretical probability. Okay, we know that a number cube has 6 sides to it. Normally 1, 2, 3, 4, 5, and 6. So there's 6 possible outcomes. We know the probability of landing on 5 is a 1 in 6 chance. If I want to take and turn that into a percent, I divide 1 by 6, shift my decimal 2 places to the right, and I'm going to go ahead and round that to the nearest percent and say that that's about a 17% chance of landing on 5. Now, experimentally, it said that 20 times the number cube was rolled, so that was the total number of times, and it landed on 5. It's told us right here 4 times. So 4 out of 20 times it landed on 5. We can reduce that by dividing both 4 and 20 by 4, and we get 1/5 of the time. And if we want to get a percent for that, hopefully we remember these from doing our rational numbers of the week, we're going to get 20% of the time. Now, when we compare 17% of the time to 20% of the time, we can tell that those were very close. So we would simply say the theoretical and experimental probabilities are close. And I'm kind of just doing shorthand here. All right, part B says, what is the probability of not landing on 1? So let's start with theoretical. There's still 6 outcomes on that number cube. How many of them are not 1? Well, 2, 3, 4, 5, and 6 are not 1. So 5 out of 6 of the outcomes are not 1. If we want to take and get that into a percentage, 5 divided by 6 gives me 0.83333. Keep going. We'll just round that to the nearest percent. So we're going to say about an 83% chance that you will not get 1. Now, let's look at our experimental probability. Again, it said it was rolled 20 times, and it landed on 1 2 times. Now, this is where you got to use your noggin, 7th graders. If it landed on 1 2 times, then that means it did not land on 1 the other 18. So 18 out of 20 times it did not land on 1. We could reduce that fraction by dividing both by 2, and we get 9/10 of the time. And if we turn that into a percent, we're going to get 90% of the time it did not land on 1. Again, our theoretical and experimental probability are quite close. So we would just again say the theoretical and experimental probabilities are close. Okay? All right, let's try another one like that, and then we're going to do a little prediction stuff. Number 2 says the spinner at the right is spun 12 times. It lands on blue 1 time. Part A asks, what is the experimental probability of the spinner landing on blue? So we know theoretically there are 4 outcomes with one of them being blue. But part A is asking for the experimental probability. So it says they spun it 12 times. That's what actually happened. And it says it landed on blue 1 time. So there was a 1 in 12 outcome of that happening. And if we turn that into a percent, that's going to be about 8% of the time it actually landed on blue. Now look at part B. It says compare the experimental and theoretical probabilities of the spinner landing on blue. If they're not close, explain a possible reason for the discrepancy. Well, theoretically in this situation, there are 4 outcomes. One of them is blue. So we would say there's a 1 in 4 chance of spinning on blue, or 25% of the time you should theoretically land on blue. However, in part A, we found that experimentally, they only landed on blue 1 in 12 times, or 8% of the time. Now, those 2 different probabilities are not nearly as close as the other ones we've seen. So our possible reason for this could be that there were not enough trials. There were not enough spins made, okay? So the discrepancy could be because there weren't enough spins made. Now, if we continued to spin this spinner, let's say 30 times, 40 times, 50 times, 100 times, we would start finding that our experimental probability of landing on blue would inch closer and closer and closer to 25%. Why? Because ultimately the numbers don't lie. Eventually, the probability would line up with the odds or close to it. Okay, look on down at number 3, and now let's practice making some predictions. It says the frequency table shows the results of a survey of 70 zoo visitors who were asked to name their favorite animal exhibit. So over here, we have bears, elephants, monkeys, penguins, and snakes. And the frequency shows how many people chose those animals as their favorite animal exhibit at the zoo. Okay? Now, we're going to use this to predict, based off these outcomes, how many people might choose a specific animal in the future. So this says, suppose 540 people visit the zoo. Predict how many people will choose the monkey exhibit as their favorite. So here's what we need to do. First of all, we need to come over here and we need to figure up how many people had been to the zoo. It told us right here that there were 70, so that saves us a little math right there, okay? So there's a total of 70 people that were polled at the zoo about their favorite exhibit. Now, according to this, if we're focusing on the monkeys, 21 out of 70, that's how many chose the monkey, okay? So I can use this as a ratio to say, okay, if 21 out of 70 people liked a monkey, then how many people out of 540 would like a monkey? Okay, now we could also figure out what percentage that is and apply it to 540 like I showed you in the earlier example. Now to solve this proportion, we can do 70 times x is 70x. And then I'm going to use my calculator to do 21 times 540, which is 11,340. And we want to isolate x, so we're going to divide both sides by 70 to figure out, and I'm running out of room here, what's new. I'll kind of put my answer over here. So 11,340 divided by 70 gives me 162. So I can predict that about 162 people would choose monkeys out of 540 if 21 out of 70 chose them in that first experiment. Look at part B. It says, suppose 720 people visit the zoo. Predict how many people will choose the penguin exhibit as their favorite. So again, originally, 13 people out of 70 chose penguins. So 13 people liked penguins out of a total of 70. We can use that ratio to predict how many people out of 720 would like penguins. So again, we can use cross products to solve this proportion. 70 times x is 70x. 13 times 720 is 9,360. And now to solve for x, we can divide both sides by 70. I'm kind of coming back and forth between my calculator. You may not be able to see all of it. And that gives us about 134 people. We can't have part of a person, so we want to round that up. So we would say about 134 people out of 720 would like the penguin exhibit if 13 out of 70 did. Okay, so again, just to kind of recap, experimental probability is what actually happens. Theoretical probability is what should happen based off of the odds and based off the number of possible outcomes. And we can use the likelihood of events that have happened in the past to predict the likelihood of them happening in the future. Now, I am going to stop my video because I hope you're kind of catching on, but if you would like to try it on your own, I will post the answer key on Remind if you guys want to do 10, 11, and 12 from page 727. You don't have to, but if you want to challenge yourself, I will show my work and show the results from that, and you can kind of compare. If you're choosing this option to show evidence of your at-home learning, you can snap a picture of any of this work we've done together and send it to me in Remind. You're going to have this lesson plus one more for next week, so I'll start working on the next video soon. You guys take care and be safe. I hope you learned something today. Bye-bye.